All right, so I guess we can start the talk. So I was the previous talk ran a little bit over. So yeah, first of all, introduction. So I'm Denis. I'm a PhD student at New York University. Also a research scientist at Facebook AI Research. I mostly work on the problems of reinforcement learning and robotics. And today I'm going to talk about the work that I've done last year. This was mostly on the dialogue systems. Let's wait for the slides a little bit. Yeah, I'll try to make it slightly faster so you don't miss your lunch. Right, so yeah. First few words about Facebook AI Research. So this is a special team in Facebook. We have about 150 people, and we mostly work on the problems of kind of like long-term AI. So not something that is going to be applicable in the, right now. Maybe more like something that's going to be relevant in the next 5 or 10 years. So we have, as I said, 150 people, and we have several offices across the world. I think the largest would be New York City and Menlo Park in California. Right, so yeah, today we're going to talk about these dialogue systems that are specialized on negotiation task. So I guess negotiation task is something, like for example, you want to buy a car or you want to buy something else and you try to get a better deal for this car. And imagine it would be nice if somebody does it for you. If there is an AI that you can just send it and it's going to get you a very nice price for your car. You don't have to do anything. Or even maybe slightly simpler example, imagine you need to book a meeting, for example, for a lunch or a dinner, and each human has an AI that these two AI can just talk to each other and arrange a meeting for you so you don't have to do anything. So yeah, we're going to discuss the baseline model. Then I'm going to tell you what are the issues with this model and how we can solve these issues. So yeah, I guess I kind of already give you a few reasons why negotiation is an important task. But I guess from AI perspective, the reason it's important because it has two aspects in it. One is how do you generate language that human can understand, and also it has this part where you have to think about long-term strategy, right? Because when you negotiate, you're trying to, you have to, even sometimes you have to bluff, you have to do some tricks that make your partner uncomfortable or to get a better price. And I guess actually bluffing or lying, it's very difficult skill to learn. Humans can only learn this at age of 4. So for example, kids younger than 4 years old, they cannot lie. They only learn it after. So this is kind of very difficult question, very difficult problem for AI. And we actually seen several examples where our model actually learned this skill to bluff, which was kind of very exciting. But yeah, if you don't trust me that this negotiation is very important, you can maybe read this book by American president. All right. So I guess another important aspect is the negotiation is kind of twofold. It can be both cooperative, where you're kind of trying to come up with a compromise, but from another point of view, it's also very strongly adversative, because it's kind of two partners in a dialogue. Essentially, they have different goals each other, and they're trying to reach their goal no matter what. So in order to study this negotiation problem, we designed the following framework. So imagine we're going to have two agents. Could be humans, could be AI. And these two agents, they have a common goal. They have different goals, and you don't get to see a goal of your opponent. So after you've been shown this goal, you're going to start talking to each other until you reach agreement or disagreement. After that, you're going to reveal independently and simultaneously this, essentially what you're going to say, what is your preposition for this deal, and if your preposition is compatible between each other, you're going to get some reward. If you didn't agree, you're going to get 0. So to give you some more context, let's imagine this simple task where you have to divide objects. So let's say we have 3 different object types: hats, balls, and books. And we have a same set of objects for each dialogue, but different objects have different values for different people, right? So for example, for the for the blue guy, let's see, book costs 1 point, hat costs 1 point as well, and ball costs 5 points. So basically, if you want to get an object, you better get a ball because it is going to give you 5 points. From another point of view, the green player, maybe, I guess for him it's important to get all the hats, because otherwise it's going to get 9 points. So they don't get to see the values of each other, so you don't know what is important for your opponent, right? But you know only the quantities of all the objects. So you can start talking to each other until you, for example, in this very simple dialogue, you would say, I want to get balls and hats, and then the green player disagrees because he also needs hats, and so forth. At some point they agreed on the deal, and they would propose the outputs, right? So the blue player would say, I want to get 2 books, 1 ball, and the green player is going to get 3 hats. So this output's compatible, meaning that they're going to take all the objects, and there is not going to be overlap. So that's why this is a valid preposition, and each of them is going to get some reward. So in this case, green player is going to get 9 points because he got 3 hats. Each hat cost 3 points, and the blue player is going to get 7 points, respectively. So, yeah, these dialogues can be rather complicated. So in this dialogue, you can see that their strategy changes over time. So sometimes, I guess, at some point they don't have an agreement. So one player treats to go away, meaning that they both going to get 0 points, and then green player actually kind of weakens a little bit, and they come up with a solution. So what we did, we basically asked humans to perform this task. So we used Amazon Mechanical Turk. So we collected about 6,000 of such dialogues. So the dialogues, as I said, could be rather complex. For example, the average number of sentences in a dialogue is around 6.6, and the sentence is also kind of longish. So agreement is very high, so that means humans very good at this task, right? So it's obviously it's not very complicated task for a human, but might be not as easy for AI. Also, we computed this Pareto optimality factor. That means you cannot get better score for yourself without lowering the score for your opponent, right? So these dialogues actually pretty optimal in terms of Pareto optimality. So that was very good for us. All right, so the simplest way we can do to model all of these things is let's just use simple model, let's just use end-to-end approach. We will take RNN model, something like this. We'll have encoder here at the bottom. So this encoder would encode values and counts for each object. It just could be simple, fully connected neural network. Then to model language, we would use simple RNN, could be LSTM or whatever, it doesn't really matter. So this model will learn to understand the context, and it will learn to produce and understand the language. And then at the very end, we would just have a softmax classifier over all possible actions. And then we would sample from this classifier, and then if the action is compatible, we're going to get some score. If not, we're going to get 0. So yeah, this model is rather straightforward. And I guess we would train it just using simple supervised learning, optimizing maximum likelihood. Obviously, the issue with this model is just it's going to basically do whatever it's seen in the data set. It's not going to go beyond human strategies, which is something that we don't want to. We want this model to be better than human. And one way to improve it is actually use reinforcement learning to kind of like optimize the performance of on the task. So one way to work it, you would pre-train this model in a supervised way in the language on your training data set. And then you would take these two models and you kind of like let them play against each other. It's sort of like self-play type of things, similar as DeepMind use it for example, for AlphaGo. So they would like play each other many times, and after each dialogue they would get some reward. You would back propagate it using policy gradient or whatever, and you would update. So eventually these models will learn to do very well on the tasks. They will learn to get a much higher score than originally they did. But there is several issues with this approach. So unfortunately, because there is no clear, because we use one model to do both strategy and the language generation, it's very hard to learn this like interesting representations of the language. So for example, our model is going to think that, so for example, let's say we have this context, 2 books, 2 hats, and 1 ball, right? And let's take a look at the first 2 sentences. One sentence has essentially says, I'll get 2 hats and 2 books, right? And second sentence says, you get 2 hats and 2 books. So in terms of the language form, this sentence is kind of like similar. They have only one different word. But in terms of meaning, it's like completely different thing, right? So that's why you have this problem where your representations that you learn, they only kind of like catch the form rather than the meaning. But we want to sort of like learn the meaning of the phrase. So it would be much nicer if our model tells that the first and the third sentence is the same, even though they have different forms, but they represent the same thing. So that's one issue with the current model. Another model is that using the any reinforcement learning algorithm in these settings is very challenging, because here we treat each word as an independent action, and number of words could be quite big. For example, 1,000 words in your dictionary. And then also when you generate a sentence, you have to do this strategy of multiple actions. So meaning is just your search space is very large, and you would need a lot of samples to actually find something interesting. And probably the most, I think, controversial issue was that after a while, when you train these models, they would forget how to speak human language, right? Because they don't care about human language anymore. The only thing they care is just how to maximize reward. And that was the problem. So I guess maybe if you remember last summer, there was a bunch of news that Facebook had to shut down AIs because they learned their language, and like human couldn't understand it. So actually, like the funny part is, for this dialogue, it's unreadable for us, but the bots get in very high reward, so they do understand each other. They can. This is kind of like valid channel of information, channel for communication for them, and they do very well. All right, so obviously we want to fix this because that wasn't our goal in the beginning. So I guess the next step we can take is let's just try to separate our model. So we use one model, right? And let's try to separate it into two modules. One module would be responsible for strategy, and one module would be responsible how to communicate the strategy. It's like in a human analogy, you would have like brain model and the mouse or tongue model, right? Right, so that sounds easy. How we actually do this? So in terms of like, if you write down some math, so you can represent your model as this conditional probability distribution. So you have essentially some context, and you're trying to generate a sequence of words. So what you can do, you can do something kind of like latent. You can essentially factorize this probability distribution into two probability distributions by introducing a latent variable. We call it Z here. So essentially what we're trying to do, imagine if we have like many, infinite amount of strategies, right? What if we try to somehow cluster these strategies, right? There is obviously like some strategies similar, some strategies different. What if we do just like simple clustering? And each cluster we would represent as an independent latent variable Z. Now, if you take one of the Z, if you sample one of the Z, so this Z should represent which strategy you have to follow at the end of to continue your dialogue, right? Okay, so that's cool. So how do we do this? There is like several ways to do this clustering. One way that's been proposed in the literature is to actually cluster by the sentences form. But that actually is not very good for us because it's going to lead us to the same issue that we had before. This just the model learns this entangled representations. Instead, what we propose is let's actually encode into this discrete latent variables. Let's encode how this variable, if you like select it, how it's going to affect the rest of your dialogue, right? So I guess, one good analogy is actually going to be strategy, right? So you pick a strategy, you think you're going to follow this strategy at the end. Later on, you can change the strategy if needed, or you can just stick with it. So that's going to be nice if we have something like this. So if you model these latent variables like this, you're going to have this nice property. So before, in the example that I show you, so we had that Z variable would capture the form rather than the meaning. But if you train actually in such a way, when you maximize likelihood of the future of your dialogue rather than the form, you would get this nice properties. So see here is just first sentence is now independent from different clusters. So now this cluster is actually represent two clusters represent different strategies, which is kind of cool. All right, and the way you learn it is kind of like a lot of math. You don't have to understand it. For those who is interested, you can read the papers later. But essentially what we do, because we need like clustering on latent models, so there is a standard approach you can use. It's called expectation maximization algorithm. It's, I guess, the simple analog would be the k-means. It just k-means work when you have Gaussian distribution. Here you have a slightly more complex distributions. So the way you're going to do it, you're going to do forward pass on each independent Z variable. You would take the one that's actually going to maximize the likelihood that you see in the above. It's maximizing likelihood of the rest of the dialogue, essentially the action you're going to take and the sentences that you're going to generate. And then for the max one, you would just backprop it. So it actually is not as expensive because you still need to do one backward pass, but many forward pass. But usually forward pass is much more faster. And the way that this model is going to look, it's kind of very similar to sequence model. So you're going to have encoder. This encoder is going to have this like discrete bottleneck. It's that all the information that you're going to communicate is going to be passed through these latent variables, and you're going to have decoder. Decoder essentially is going to take this latent variable and produce a sentence that describes this latent variable. So let's say we have this encoder that learns the latent variables and distribution over them. Now we need to train a language model that's going to understand this latent variable and it's going to do like a very good job explaining the latent variables. So to do so, we're kind of using, actually like very similar to the previous talk, we would do this like information leakage. So we would feed to decoder the future state. So essentially we would give him the sentence that it needs to produce, but the sentence is decoded through this latent variable. So essentially we give all the information that is needed. You just need to learn how to parse this. So we would train this language model like this, but now the problem is how we're going to do this at the inference stage, where we don't have to see the future, right? So you don't know what's going to happen. So for this one, we can do something very similar to, and it's like variational autoencoder. We can learn this reconstruction laws. So essentially we would try to reconstruct the probability distribution over the future states. It's not going to be as good as the original one, but it's fine because we're still going to tune later this model. And that's our full hierarchical model. All right, so here's a few examples of, so what I did here, I take this model, I sampled 5 clusters from it, 5 different clusters, and for each cluster I sample the sentence that it represents. So on the left side you have a baseline model that didn't use the way we optimized latent variables through the expectation maximization algorithm. So as you can see, there is no structure on the left side. So each cluster can have a different, it's kind of like the sentence is not compatible. I guess here for details, so all of these examples are relevant for the set of 2 books, 1 hat and 2 balls. So if you, let's take a first example, for example, for the full model. So the first sentence says, I would like the hat and 1 book, right? And second says, I cannot give up the hat, but I can offer the book and 2 balls. So if you actually subtract what it says from this set, you're gonna get the meaning of the first sentence. So, and that's why we have this like nice property clusters represent different strategies. And we have a language model that can kind of like use very generic language to represent its strategy. So it doesn't always generate the same sentence. It can generate different sentences, but this sentence is going to have the same meaning as all the other sentences within this cluster. So that's, I think that's the main contribution of the work. So if we directly apply this model, we can see that its language quality of this model is much better, so we can achieve a lower perplexity. The lower perplexity, the better your language. We also see that end-to-end reward is also much better. So for example, our full model can beat all the other models, which is nice. So next step is now we can actually apply reinforcement learning to improve performance even more for this. So as you remember from the baseline model, the main problem was that the language would, when we apply reinforcement learning, the language would diverge. To avoid this, we would just, we would just freeze the weights of the language model. So we're not going to change language model anymore, and we don't need to do this. We only need to change the way we generate strategy, right? So that's kind of like analogy, if your human knows how to speak, you don't have to teach him to, I guess, kind of like different language, you better just teach him how to negotiate. So you have to improve his brain rather than his language. So now what we can do, we can just update only encoder part, and discrete variables also are going to remain the same. We're going to have the same clustering for discrete variables. So essentially what we need to adjust is the probability distribution over clusters, and that we can easily do with the standard reinforcement learning algorithm. So probably the main result of this work is this graph. So I'll try to parse it for you. So here we plot the reward you're going to get against perplexity. So as I said, the better perplexity, the better your language. So if your perplexity is going to the right side, so for example 6.4, language becomes unreadable. So what we see, our model, which is green here, can get higher reward with lower perplexity. That basically means we can get higher reward with better language. Ultimately, if you keep training, let's see, baseline model, it's going to get higher reward, but it's going to produce this like a meaningless language which humans don't understand, and we probably don't want to use that. So essentially, like the left part of the graph is very important. So we have this nice separation in reward while still maintaining the good quality of the language. Another kind of like easy win for this model is that we have is, imagine if we're gonna kind of like using this model to plan ahead. So one way to plan ahead is just like to sort of like Monte Carlo samples. You would sample a few dialogues until the end, and you can estimate the points you're gonna get. So the problem with baseline model is all the samples, they're gonna look very similar because there is no kind of like diversity in it, because we learned how to mimic the form. And that's why you're not gonna explore the search space a lot. So you see all of these samples result in the same dialogue. So with the new model, what we can do, we can actually instead sample the strategy first. So we can sample different Z's. So that means different clusters. Now each cluster we know that represents different meaning. So all of these future dialogues, they're gonna have a completely different structure and completely different meaning. And you can get very diverse continuations of the dialogue. That means you're gonna explore the search space much more efficiently, and you're gonna find like, you can get a better estimate of your future reward. Right. So this actually helps a lot, as you can see. For example, what we do, we take on left side the diverse rollouts model, on the right side we get no rollouts model or baseline rollouts, and we just like let these two models to play against each other for like 10,000 of dialogues, and we see who beats what. And as you can see, the diverse dialogues, they can get much higher reward. All right, and I guess the ultimate test would be to use this model against a human. So what we did, so we put several models. There was a, let's see, baseline model, which is just RNN. Then we added, and we have our model, which we call full. Then we have a variant where we update it with reinforcement learning, and then we have another variant when we use this planning with rollouts. And so we use one of this model, we randomly sample one of this model on one side. On another side, we have a human. So we use mechanical Turkers who just have to play this task with the models. They don't know that they play against humans. And in fact, some of these models on the left side can be human too. So this is human against human, can score 6.64 points, which is quite good. So it's kind of like the best result of all of them, but the first model, RNN rollout, can actually outperform human. So in this particular task, we can get we can do much better than human, which is kind of surprising. So I think this is kind of like good suggestion that our model works. Obviously, like the scope of this task is maybe not as complex as all other tasks that human can do, but at least in this simple task, we can outperform human, which is a kind of nice step. And this is, for example, one of the dialogue that's sampled from the model. So as you can see, it produced very interesting and the complex strategies. So it doesn't, it's kind of like, it can do like a lot of steps. It can change the, it can change the flow, it can change strategies, and at the end it gets very good score. All right, so yeah, to conclude, so yeah, this talk was based on these two research papers that was presented, one in 2017 at EMNLP, and the continuation of this at ICML this year in Stockholm. So yeah, if you need more details, feel free to go to these links and read the technical details about how we exactly, because I omitted obviously a lot of details from here, so you can access this. And also we have a open source implementation, and there is data set in there as well, so you can try to play with data set, and you can have a exemplar code for the baseline model at least. With that, I guess I want to conclude. So yeah, if you have any questions, feel free to ask me.
there is one column, language quality, and just interested how do you measure language quality?
Yes, so we measure, so one, I guess, simple way to measure is language perplexity, but that's not a very good way. So in fact, when we did a human test, we asked each human to, after the dialogue, we asked to rank, like give a mark from 1 to 5, how good was the dialogue. Was it like AI? I guess the scale was like 1 if it's obvious AI, 5 it's obvious that human. And if I scroll back, as you can see, so human can say, can give like, when human plays against human, it gets 3.85. But sometimes it's like, for human, it's not obvious that he's talking to another human. And I guess we can get a 355 the best, so which is not far away from the human-on-human interaction.
Thank you for the talk. I have a couple of questions. So you said that you're working on solving AI and working on something that will be useful in 5 to 10 years. So I'd like to ask you, how do you make sure that it's actually going to be useful in 5 to 10 years? Because I mean, it's really hard to predict what's going to be useful or not. And for example, you gave the motivation for your talk, right? And the motivation that 2 agents will talk to each other, right? And they will schedule an appointment. But then why do you want them to speak human language? I mean, that's not necessarily true, right? So,
exactly.
could you elaborate?
That's a good question. So I guess maybe I'll answer the second question first. So I think it's important for a human to understand what AI does, right? So if you don't understand what is going on, like, people's going to go crazy, right? So and right now this is a big problem for all of these machine learning things, like algorithms. It's just you have some simple model of linear regression or like even decision trees where you can kind of like get understanding of what's happening, but once you go to the neural networks, there is no way you can understand what's happening. And that's why it's, I would say like language here is kind of a good debugging tool. So you can kind of like, you see that what language you produce, you see what it means. Yes, maybe it's not the most efficient channel for two AIs to communicate, but we need to have, as a human, we need to have a way to understand like a deep level what is happening. If we don't have this tool to do in our hands, it's going to be very, it's going to be very challenging. Like imagine you have a self-driving car, sometimes it just like turns left suddenly. You need to know why. The rest is going to be unmanageable and very dangerous. The first question, yeah, I mean, it's a hard question, so we hope it's going to be useful. So, for example, we have already evidence that some of the work that we do is very useful. For example, machine translation, image classification. There has been a lot of work now happening in healthcare, which is still a very long way to go. But yeah, I mean, it's a good question. We always just try to look at the AI is actually helpful. It's not the other way around.
Thanks for the talk. And in the presentation, the model used like a pretty simple, straightforward technique. It shows like it's trying goal, and it expected that the opponent also shows its like the main goal. Mm-hmm. Do you have like an additional layer I mean, in negotiation there are different techniques how to obtain what you want actually, and it's not always straightforward. So do you have additional layer to predict the technique that opponent is using and to choose the optimized technique to negotiate the situation?
Yeah, I guess for the sake of simplicity, this presentation just had some very simple slides of human parts. Obviously, the model that I presented is quite far away from actual models that we use. So for more details, I guess you can read the paper. But at the end, we use kind of like very complicated neural network with a bunch of moving parts. the way we encoded strategies or this context would be like we would use like some embeddings to embed this into a continuous space. Then there's going to be like some neural networks, multi-layer, perceptron, and then we have a bunch of LSTMs with have attention. So I just didn't mention this here. But you can take a look at the paper. In that, it's very detailed, hopefully clear explanation.
Hello, thank you for I have a couple of questions. First one is, you mentioned that after you created two separate models, one for language representation and second for strategic, you mentioned that you could improve only strategic way because it's the meaning, but have you tried improving the language representation and tested with humans? Because it seems like the language representation also could improve the result of the negotiations.
Yes, this is a good point. Actually, we've thought about it. I guess one strategy you can imagine is just you can do like this iterative process. We'd improve one thing, then you improve another, and we'll use reach. We haven't done this. We had planned to do this, but didn't have time. But yeah, I think this is actually valid, and that's probably something that needs to be done in the future. Because I think the biggest problem is, I would say, for the language is just so far it's like contained in the data set, so it only carries the distribution that you have in the data set, right? So it doesn't go beyond this data set. But obviously, like if you talk to some new human, they can use different words. This word is going to be out of vocabulary for you. So you have to have this like online system that's going to like incorporate new words, new settings. Yeah, so that need. I guess if the system would ever be in production, there's something like this have to be done.
Okay, thank you. And the second question is, you displayed on one of the slides a situation that some of the products had different value for agents. And what if the product has equal value for both agents, and how it would influence
there has been cases where they have identical values. So in that case, they would just have to somehow compromise, like somebody, because like the simplest way they can do, they just can disagree and they're going to get 0 points each, right? So somebody have to go and compromise, right? Somebody have to agree to get less points than one. So yes, but I guess like we make sure that we don't reveal the points for each object, because the task when you reveal this points task is much easier. This is a kind of like task with a partial information, like with like poker or some other games where you don't see the information, you don't have all information about what is the opponent doing. So this is much more complex task.
Okay, and the last question. Do you plan to improve the performance of this model, and do you see any ways for future integration?
Yeah, I guess, this has been done like a year ago, so since then there's at least a few major things happening in like NLP community. I think the biggest one was the Almo embeddings. So I think if you just input that here, performance can improve just automatically. But I think like beyond that, you would have to, I think the easiest way to go is collect a bigger data set, like more diverse data set, and have bigger models.
Thank you once again. Very good.
Maybe this is the last one, okay?
Thank you for your talk, and simple question just for clarification. When you train your agents, they get the value, value what they get is their individual responses on all the sum of responses to Yarats?
It's a sum.
It's a sum.
It's total reward.
Okay, and then when this question, when the result of the one agent can get is greater than the sample for what you get. For example, one agent is the maximum that he can get is 6, and the result of the second will be 4, but the second alone get 15 points.
Yeah.
What will the model choose and what priorities? What will it prioritize?
So because like this is, I mean, let's see, this model which, because it like for each score, how much you get, you also sort of get like probability, how likely you're going to get 15 points, right? So obviously 15 points probability is going to be probably very small because it's very unlikely you're going to get 15 points. So it converges to something that is more likely.
So we will choose something between.
So you would essentially like the model outputs probability distribution over all possible outcomes, and then you would sample. So if this probability distribution put more mass on the, let's say, 6 points, then most likely you're going to sample 6 points.
Thank you.
Thank you, Denis. Round of applause for Denis.